Hello, students. Now we will continue with our part 2 of module 5 of our Fundamentals of Artificial Intelligence course. So, as you know, module 5 is about learning concepts. So, in our previous video, we started with what is learning and we looked into rote learning, learning by taking advice, and learning by problem solving. Now, we will mainly concentrate on learning from examples. So, what is learning? The act, process, or experience of gaining knowledge or skill. Or we can tell like behavioral modification, especially through experience or conditioning. Now, in this video, we will look into learning from examples, that is induction. So, in our everyday life, we often learn concepts simply by observing the examples, right? Rather than studying formal definitions. For example, if you're considering a child learns what a car is by seeing many cars, different colors, different sizes, small cars, large car, different colors, likewise, right? And gradually, they will try to understand the common characteristics such as wheels, doors, and the movement. So in artificial intelligence, this process is called classification. So classification is the process of assigning to a particular input the name of a class to which it belongs. So classification is an important component of many problem-solving tasks. Before the classification can be done, the class it will use must be defined. So, for example, if you're considering an email system, it classifies messages spam or ham. The medical system also classifies patient as healthy or deceased. And a facial recognition system, you can tell like it classifies images as belonging to specific individuals. So before classification can be performed, the system must define what each class represents. So constructing these definitions from examples is called concept learning or induction. This can be done in the way isolate a set of features that are relevant to the task domain, define each class by a weighted sum of values of these features. Each class is then defined by a scoring function that looks very similar to the scoring functions often used in other situations. So another approach is structural approach, which define classes based on how components are arranged rather than only on feature values. And first approach is identifying the relevant features, and second approach is structural approach. So the Winston Learning Program demonstrates concept learning using structured objects. So the goal is to construct the representation of the definitions of concepts in this domain. So in this case, concept is house and brick is rectangular block with a wedge that is triangular block suitably placed on top of it, tent two wedges touching side by side and an arc two non-touching bricks supported and third wedge or brick is learned. So idea of near-miss objects that is similar to the actual instances which was introduced. So in this case, imagine teaching a child to recognize a house using toy building blocks. You know building blocks, right? So a house may consist of a rectangular block representing the walls and a triangular block representing the roof placed on top. Similarly, in the case of instant program, learn concepts such as house, tent, and arc by analyzing the arrangements of blocks. So, the main idea introduced in this program is the concept of near miss objects. So, what is a near miss? A near miss is an example that resembles the target's concept but does not fully satisfy its definition. For example, a structure with walls, okay, but without a roof, but might look like similar to a house, but is not actually a house. So by comparing the correct examples with the near misses, the system tries to identify which features are essential. Basically, the system will try to identify the features which are relevant. So humans may use this strategy as well. Like, for example, if you're considering students learn what constitutes a correct answer by comparing correct solutions with the incorrect ones. So input was a line drawing of a block's world structure. Input process to produce a semantic net representation of the structural description of the object. So links in network include left of, right of, does not marry, supported by, has part, and essay. These networks or these links can be seen in the next slide. Okay, the marry relation is important. Two objects with a common touching edge are said to marry. Marrying is assumed unless does not marry state. So in this system, the input consisted of line drawings of block structures. The program processed these drawings to produce a semantic network representation. Okay, so humans also rely on the relationships in order to understand the objects. For example, if we want to recognize a chair, not just by its parts, but by how the seat is supported by legs and connected to a backrest. So, an important relation called marry indicates that the two objects share a common touching edge. Okay, for example, two blocks placed tightly side by side are considered as connected. So, understanding these relationships enables the system in order to recognize the complex structures, even when individual components vary. So in this, we can see all the links which we discussed in the previous slide. That is left of, right of, supported by, has part, does not marry, is a. All these are semantic representations. So there are three basic steps to the problem of concept formulation. That is, first one is select one known instance of the concept. Next one is call this the concept definition. Next one is you have to examine the definitions of other known instance of the concept. That is generalize the definition in order to include them. Next one is to examine the descriptions of the near misses. That is restrict the definition in order to exclude these uses. So concept formation typically involves three major steps which we said now. First one is in order to select the known instance of the concept. Okay, this is the concept definition. Next one is to examine the other known instances and to generalize the definition. Third one, we have to examine the near miss examples. So likewise, in this case also, human follows this process naturally. For example, when learning what qualifies as a good project report, that is, students observe high quality reports, identifying common features such as clear structure, proper formatting, and then avoid mistakes seen in weaker reports. Through repeated refinement, the concept becomes more precise and reliable. So this diagram shows the comparison of two arcs and the arc description after the examples. So uh, we can see this as nodes A, B, C, D. So these are the parts of the structure, and you can see relationships, that is edges or arrows, that is how parts are connected. So this is the main way to represent knowledge logically so AI systems can understand the structure. So if we look into the first diagram, that is 17.4, you can see four objects A, B, C, D, and the other objects are brick, wedge, and key. Okay, so if you are seeing has part means, for example, A and B is connected. So with has part, then now you can tell like A has part B. So and A supported by B. Okay, B left of C, D right of C. Likewise, you can interpret this diagram. So what is the main purpose or main objective of this diagram? It mainly tries to show that two arcs may look different physically but can share the similar structural relationships. So AI mainly uses this to understand structural similarity instead of just appearance. When we look into the second diagram, okay, This diagram shows a generalized arc concept. Okay, after seeing multiple examples, AI learns what features define an arc. For example, arc has a top part. The top is supported by two sides, that is B and D. There may be an object under the arc, and left and right supports a position related to each other. These are some of the key rules or key assumptions. Okay, so what is the real meaning for that? AI learned the pattern, removed unnecessary details. Okay, so mainly this diagram shows how AI represents objects using the relationships between different components. So the first figure mainly compares two different arc structures using the spatial relations like supported by left off, ESA, has part, like that. The second figure shows a generalized arc description learned after observing the multiple example. Okay, after the multiple example, what is a generalized form? So this mainly allows the artificial intelligence system to understand the structural similarity rather than the shape similarities. So in this slide, it describes about the arc description after a near miss. So this is one of the classical concept in AI learning or knowledge representation. So what do you mean by near miss? It is an example that is almost correct but fails to satisfy the definition. For example, a structure looks like an arc, but one important relation is missing or incorrect. So AI uses near misses to refine or improve its learned concept. For example, in this diagram also, as we see in the previous structure, we have four nodes, that is A, B, C, D, and we have other elements like brick and object. Okay, now here also you have relations like has part supported by left off, right off, and easy. So what changed after the near miss? That is, we can observe that a similar structure that failed to be a proper arc. So in short, you can tell like this diagram shows how AI refines the concept of an arc after observing a near miss example. So a near miss is a structure that closely resembles an arc but fails due to some missing constraint. For example, after analyzing this, AI identifies essential relationships such as support and the positioning after improving its understanding of the each arc concepts. Now we'll see what is explanation-based learning. So EBL is based on the hypothesis that an intelligent system can learn a general concept after observing only a single example. By understanding why an example is a member of a concept, can learn the essential properties of the concept. So explanation-based learning focuses on understanding why an example satisfies a concept rather than simply memorizing it. So, for example, if you are considering learning a scientific law, if you understand the reasoning behind it, you can apply it to many different situations without memorizing individual cases. For example, learning to repair electronic devices. Okay, once you understand how circuits work, you can fix it very easily. So, in the case of artificial intelligence, explanation-based learning uses prior domain knowledge in order to analyze a single example deeply and extract a general rule. So that is what it is written here. EBL uses prior knowledge in order to analyze or explain each training example in order to infer what properties are relevant to the target function and which are irrelevant. So this method is particularly useful when we have only few examples are available but strong background knowledge exists. So in this case, we have four inputs, that is called concept, training example, domain theory, and operationality criteria. Training example are the facts, domain theory are the inference rule, and goal concept, we will have some predicate statements. So we have four inputs and we have the task is to determine a generalization of the training example that is sufficient concept definition for the goal concept and that satisfies the operationality criteria. For example, if you are considering an example for explanation based learning. We have a robot, okay, and it learned how to stack boxes safely. So by analyzing one successful stacking operation, it understands the principles such as how to balance and support. So the robot can apply the same knowledge in order to stack different objects in the coming future. So humans are also behave in the same manner. That is, after learning to ride one bicycle, you can ride other bicycles, right? Because you understood all the principles of balance, steering, pedaling, and how to move forward. So, in this case also, in explanation-based learning also, it transforms the detailed understanding of one instance into knowledge applicable to many other situations. Okay. So this diagram, uh, first diagram mainly explains about the explanation and after learning. And second diagram explains about the explanation-based learning process. So first diagram, that is in explanation and after learning, what it does is that this illustrates how problem solving changes before and after the learning process. For example, in the upper part, detailed proof of goal, the system starts from the basics facts at the bottom and moves through many intermediate reasoning steps in order to reach the final goal. So the process is similar to how a beginner solves a mathematics problem. For example, that student will write each and every step, including all the formulas, substitutions, intermediate results, in order to find out at the in order to arrive at the final stage. So each time the problem appears, the student must repeat the entire reasoning process. So in the case of artificial intelligence, this represents a system that has knowledge but has not yet learned an efficient shortcut. So after the learning process, that is the second diagram, the system can go directly from the facts to the goal without repeating all the intermediate process. That is, the learned knowledge act as a combined role. For example, if you are considering a real life situation, like you are trying to learn a multiplication, what will you do? For example, if it is a child, the child may compute 7 times 8, right? By repeated additions, adding 7 times, 7, 8 times, right? So after learning the multiplication table, the child directly recalls the answer without recomputing it. Okay, so this explanation-based learning converts a complex reasoning process into a direct solution by improving the efficiency. Okay, the next diagram, that is the next diagram, the flow chart, it depicts about the explanation-based learning process. Okay, so how it generates a new rule from a single example. At the top, we can see domain theory, right? This represents the prior knowledge about the subjects, all the rules, principle, relationships, which we already know, or the knowledge base. Okay. Next, we consider a specific example stated as X is P. Okay. For instance, you can suppose X is a particular object and P is a property. Okay. In this object is safe to stack, or you can tell like the medicine cures the disease. Okay, so using our domain knowledge, the system performs a complex proof in order to explain why X satisfies property P. Okay, we will try to find out the why part. Okay, so this step mainly involves the reasoning through the known rules, which we already know, which we already fed in the domain theory. So, for example, a doctor might analyze why a certain treatment worked for a patient by considering symptoms. Okay, so symptoms, as well as he will look into the medical history or all the mechanisms. So the result of this reasoning is an explanation, or it is type of a proof. Okay, so the system try to generalize this explanation to create a new domain rule, right? Object similar to X will also have a property P. So In the case of a real life, how humans learn different principles. For example, if you learn that a particular type of key opens a lock because of its shape, you understand that other keys with the same shape will also work, right? So, for instance, after learning how to solve one type of physics problem, a student can solve similar problems quickly by applying what? The same principles. So likewise, the explanation-based learning will transform deep understanding of one example into a general rule that simplifies the future reasoning. That is, we will have a domain theory, and based on that domain theory, we will try to prove something with the help of the reasoning. Okay, and the output will be an explanation or generalized form. Now we'll see one example for ABL. We have input examples, domain knowledge and goal. So this example clearly explains how artificial intelligence uses the input examples, domain knowledge in order to identify a object category. So B is a bucket if B is liftable, stable, and open vessel. If these three conditions are satisfied, then you can tell that B is a bucket. So first input examples describe the object properties. Okay, it is deep and its color is green. Okay, so and where Y is a thin material, any thin material. So next domain knowledge defines the rule, and for example, an object having a handle is liftable. And you can tell like having a flat bottom makes it stable. Next one, upward pointing opening makes it an open vessel. So these are the different rules which is already saved in a domain knowledge. So if these conditions are satisfied, then you can tell that my goal is satisfied. That is, if B is liftable, stable, and open vessel, then B is a bucket. Okay. Finally, based on these properties and rule, the system can conclude that object is a bucket because it satisfies the rules. So this diagram shows the structural description of a concept called bucket, right? In the previous slide, we understood that if B is liftable, stable, and open vessel, then B is a bucket. Likewise, the bucket is defined using the three main properties, right? Liftable, then stable, and open vessel. If it is stable, it has a flat bottom. Okay. And if it is considered as an open vessel, if it has an upward pointing opening. So by combining these structural properties, the AI system identifies and represents the concept of a bucket. So concept mainly describes about the structural properties or structural description. By this, we are concluding part 2 of our module 5 learning concepts. Now we will move to part 3 of module 5. So thank you.